Hello, my one attendee so far. Okay. So I am going to be going through the series circuits notes that are up on Canvas already. They're in a PDF, and I'm going to kind of like annotate them as I go. It just kind of helps me make sure that I get everything out that I want to. So let's go ahead and get started. Okay. So when we talk about a series circuit, just like when you have a series of numbers, it's one right after another. And when we're talking about one right after another, it's one resistor right after another. So the resistors are connected end to end. And as you can see in the diagram, there's only one loop for current to go through. Okay. And I'm going to see, I don't have like a laser pointer option. That would be really cool if I did. Hold on, let me get out my pen. Okay, so we have one loop for current to flow through, and that's going to be really important for us as we move forward in discussion of like how are we going to analyze this circuit. So Kirchhoff's loop rule, which is the idea that energy or voltage is conserved in a circuit. Kirchhoff's junction rule, which is the idea that charge or current must be conserved in a circuit, and Ohm's law all still apply. So everything that we've been talking about still is going to hold true in this kind of circuit. We're just going to kind of take it to the next level and analyze it a little bit more because we've looked at circuits with one resistor. Now we're going to look at circuits with multiple resistors. All right, so let's talk about current first because that's probably the easiest thing. So that's based off of Kirchhoff's junction rule. And basically this says that any current coming out of a single point, in this case the battery, has to equal the current flowing out of that single point, in this case the battery. So in this type of circuit, as I showed, there's only one loop for the charge and therefore the current to go through. So we're not going to be losing charge or losing current as we travel through this circuit. We're not going to be like leaking charges, so to speak. So what that means is if there's only this one loop for the current to travel through, then that must mean the current has to be the same everywhere. So the current coming out of the battery here is going to be equal to the current through the resistor here, equal to the current through this resistor, and so on until we get back to the battery. And that current is going to be the same everywhere. So the amount of charges moving through any of those points at a specific time is exactly the same because there's only one loop. Okay? It's kind of like if you were running a race and there was only one loop for the race, right? Normally in a race, people don't just like disappear, right? The amount of people running the race at any given point in time is the same, okay? Because people don't just disappear. I mean, they do if they get kidnapped, but we're assuming no kidnappings happen during this race. I've been watching a lot of Criminal Minds lately, so. All right, so here's the equation that we can use to kind of describe that current. So the idea that I battery, the current through the battery, is equal to the current through resistor 1, through resistor 2, and through resistor 3, and so on and so forth. We usually just stick with 3 resistors because it's nice and easy, but we could have 4, we could have 2, any amount. Okay, so let's talk about the loop rule now, which deals with voltage and energy conservation. So remember, this loop rule says that the voltage in the battery has to get used up as the charges travel through the circuit and before returning to the battery, because we need to have a conservation of energy. We can't return to the battery with energy and then gain the same amount of energy because that would mean we're adding energy to the system, which we can't do. Okay, so when we talk about voltage, because there's only one loop and 3 resistors, any voltage from the battery has to get used in the resistors to conserve energy. Okay, so the voltage from the battery ends up equaling the voltage and what's kind of called the voltage drop, meaning the amount of energy used in resistor 1 plus the amount of energy used in resistor 2 plus the amount of energy used in resistor 3. So what does that actually mean? Let me erase these arrows. So let's say in the battery, we gain 9 volts of energy, okay? as we travel through resistor 1, that amount of energy is going to decrease. So let's say resistor 1 is a value such that we use 2 volts of energy to get through it, right? So that means now the charges have 7 volts of energy because we are decreasing the potential drop or the voltage drop across R1 is 2 volts. Let's say R2 is a little bit bigger of a resistor. So the bigger the resistor, the more energy or the more voltage it takes to get through that resistor. So let's say resistor 2 has a voltage drop of 4 volts. So that means after resistor 2, we're left with, well, if we had 7 and then we drop 4, we're left with 3 volts. Okay? So that means that the rest of this 3 volts needs to get used in resistor 3 because we have to move back to the battery with a total of 0 volts. Okay, so we can conserve energy. So we leave the battery with 9, lose 2 in resistor 1, lose 4 in resistor 2, and then we're going to lose another 3 volts in resistor 3. Okay, and the current works itself out so that these voltage drops are perfectly, so that we have that conservation of energy. Okay, so we say that the voltage gained in the battery is equal to the voltage drop across 1, across 2, plus 3. Okay, so we add up all the voltages. All right. So then we get into this idea of equivalent or total resistance. So let's say we wanted to take those 3 resistors, and instead of having 3 resistors, we wanted to create a circuit with only 1 resistance that behaves in the same way. So the same current, essentially. So this is called equivalent resistance. We're taking those 3 resistors and condensing them down into 1 equivalent resistance. Okay. So we can use Ohm's law, the idea that V equals IR, to help us figure out what that equivalent resistance is, because we know that Ohm's law is true for not only the battery, but resistor 1, resistor 2, resistor 3, like I have written here. So the voltage in the battery is going to equal the current from the battery times that equivalent resistance. V1 is I1R1, V2 is I2R2, and so on. Notice how the subscripts are all the same. I'm not mixing subscripts. I can't do that. That'd be bad. No mixing subscripts. Okay. So we're going to use the equation for voltage, the idea that V battery is V1 plus V2 plus V3. Okay. And we're going to substitute in each individual Ohm's law equation. So V battery is I battery, R equivalent, V1 is I1, R1, and so on. So I'm just substituting in, okay, with those Ohm's law equations. Now, if you remember, because we only have 1 current loop, all of the current is going to be the same everywhere, which means that I battery and I1 and I2 and I3 are actually all the same value and therefore can cancel out. So if I go through and cancel out all the I's, what I'm left with is this equation here, which tells me how to find the equivalent or total resistance of the circuit. So essentially in a series circuit, to find equivalent or total resistance, all we're going to do is add up the individual resistors. Actually not that bad. It's really easy. And we can figure those out in different ways. So I'm just going to check for questions real quick. And it doesn't look like there are any. Nothing in the chat. Wonderful. So I'm just going to keep going. Okay. So those are kind of the 3 main equations that we're going to use to help us solve some series problems. But we know that, you know, math isn't everything. So I want to talk about some kind of conceptual ways that we can use the equations. So the first thing I want to talk about is what happens if we add or subtract resistors in this type of circuit. So in a series circuit, adding more resistors, since we're just going to tack on like an R4 and R5, is going to end up increasing the overall resistance. Excuse me. We're not going to have negative resistance because that wouldn't make any sense. So even if that resistance is very, very small, it's still going to increase the overall resistance. So more resistors in series increases overall resistance. Okay. Now, according to Ohm's law, If we increase that total resistance, okay, with the same battery, so we're not going to change the voltage, it's still, let's say, a 9-volt battery. If we increase the resistance with the same battery, that's going to end up leading to less current flowing through the circuit. Essentially, the circuit is now harder to get through, so there's going to be less current flowing through the circuit, right? Remember, current and charges are kind of like humans in the sense that they enjoy the path of least resistance. So more resistance is going to end up leading to less charges. Okay. Now, because we end up having less current with the same battery voltage, this ends up leading to less total power, less energy usage in the circuit. Remember, we talked about power on Wednesday. Power is current times voltage. So if we have the same voltage for the battery but less current, then the overall power generated by the circuit is going to decrease. So it just saves us a little bit of energy because we're drawing less current. All right, so now let's talk about light bulbs. And when I talk about light bulbs, I'm going to talk about ohmic light bulbs, meaning light bulbs that follow Ohm's law. So really just basic light bulbs that aren't going to explode on us or anything. Okay, so the light bulb brightness is based on the power of the bulb, which we talked about the other day, which is why 120-watt light bulbs are brighter than 60-watt light bulbs. Okay, so let's say we have two circuits. Circuit A has 2 light bulbs in series, and circuit B has 3 light bulbs in series. And we want to compare the brightness of these bulbs. Well, in order to compare brightness of the bulbs, we need to think about the power generated in each of the bulbs. Okay, so A, since we have less resistors in series, is going to have less resistance. Okay, so we're going to assume that each of these bulbs are identical. We're going to assume they're all identical bulbs, okay, which means they have the same R value. Okay, so that means that A has less overall resistance, okay, which means that A has more current. And we know from P equals IV that if we have more current, we're going to have more power because we're going to assume that these batteries are the same as well. Okay. So A ends up having brighter bulbs because we have more current from that lower resistance value, which means there's more power flowing through each of the bulbs. More power means more brightness. So A has brighter bulbs, but that comes at a cost. Because more power actually means more energy use over time, because remember, power, in addition to being IV, is also change in energy over time. So more power means more energy use over the same time. So that means A actually runs out of energy first. So let's say A and B were connected to 2 9-volt batteries, and we just let them go for as long as they could. A would actually turn off faster than B because A would run out of usable energy first because we have more power drawn from the battery. Okay, so in either of these situations, though, unscrewing a light bulb ends up leading to them all going out. Okay, because we no longer have a complete circuit loop. It's essentially as if we cut the wire, right? No longer have a complete circle. Okay, so in series, the less number of light bulbs, the brighter the bulbs, which is great, but that comes at a price. The brighter the bulbs, the more power, more energy usage, so we run out of energy faster. Okay, now this idea of unscrewing light bulbs leading to them all going out is actually what happens a lot of times in old school Christmas lights. So if you ever had old school Christmas lights, and either the ones that you hang up from your window or on your tree, you know what I'm talking about. Usually if one of the lights go out, then a whole entire section of the lights go out, which is the most frustrating thing in the world because then you have to go through and test each one. The reason why is because those lights are wired in series. Okay, so a single section of lights, there might be 2 sections, but a single section is wired in series. So you blow one of the bulbs, they're all out, which is why half the strand goes out when one light bulb goes out, which again is frustrating, but it's okay. Checking for questions again. It doesn't look like there are any. All right, so let's talk about actual numeric solving now. Oops. My File Explorer popped open. Okay. So in order to kind of organize the information we might be given about any given circuit, my OneNote froze. Oops. There we go. So in order to organize the information we're given about any circuit, whether it's series or parallel or some sort of combination, we're going to use something called a VIRP table. What does VIRP stand for? It stands for voltage, current, resistance, power, VIRP. So again, these help us organize the information given to us about a circuit and then help us figure out how to solve the problem. Okay? So we would fill in any individual row. So what do I mean by a row? Well, I mean going across the table like this. We would fill in any row using Ohm's law or the power equation, depending upon what information we're given. Okay. We could fill in any individual column by using the rules. Oh, you can't really see that. Let me use yellow. So we would fill in any individual column by using the rules for a series circuit. So those equations that I mentioned in the beginning. Okay, so let's go through an example. Okay. So let's say I have a circuit that's set up with 7.5 volt battery. Resistor 1 is 5 ohms. Resistor 2 is 8 ohms. Resistor 3 is 2 ohms. Okay. So I'd set up my VIRP table, and the letters in pink is the the numbers in pink is the information that's given to me. Okay. So any of the information given to me, I fill in the correct spot. So that 7.5 volts is the voltage from the battery. So I go V battery 7.5 volts. 5 ohms is resistor 1. So I go to resistor 1 and over to the resistance column, fill in 5 volts, then 8 volts, and then 2 volts. Okay. So from there, there's kind of a couple of different options. So the first thing that I suggested to do, since we have R1, R2, and R3, is why don't we just find the equivalent resistance by adding them all together? So that's what I did here in step 1. Okay, is I added up all of the resistors to find this 15 ohms. So I used the information given to me to fill in another box. And notice how I was filling in or using information in a column, so I used one of my column equations, so to speak. Okay. Then I was like, oh, well, I now have the voltage from the battery and the total resistance. So I could probably fill in that row and I could find the current from the battery. So that's what I did next. I used Ohm's law to find the current from the battery, which ends up being 1/2. Now, what's great about finding that current from the battery is that current is going to be the same everywhere. So if you look at step 3, I battery is I1, I2, I3. So I can fill in 1/2 amp for all of my currents, which is awesome. So like I did one equation, but I was able to fill in 4 boxes. All right. So next thing I want to do is, now that I have all of the individual currents, I can use Ohm's law to find all of the voltage drops across each of those resistors. Okay. So that's what I do in this next section. I use Ohm's law to find V1, V2, V3. So remember, Ohm's law is, you can't really see that, but V1 equals I1, R1. So I'm essentially multiplying R times I, and that's giving me these voltages here. Okay. So across the 5 ohm resistor, I'm losing 2.5 volts. Then across the 8 ohm resistor, I'm losing 4 volts. And across the 2 ohm resistor, I'm losing 1 volt. Okay. Now, if energy is really conserved, all of those values should add up to 7.5. So that's why step 5 is verify this V battery is V1 plus V2 plus V3. Well, 2.5 plus 4 plus 1 is 7.5. which means I am conserving energy. Yay. Okay. So I gain 7.5 volts in the battery, lose 2.5 across the first, lose 4 across the second, 1 across the third, and I return to the battery with 0 volts. Then from there, if I need it, I can calculate the power for each of the different resistors in the battery just using P equals IV. So multiplying the power times the current times the individual voltages. Most of the time you won't need to find the power, but it's good to kind of keep in there, because if these were all light bulbs, this would actually tell us which light bulb is the brightest. And according to this, since the 2 or resistor 2 is the largest wattage, that light bulb would be the brightest if they were light bulbs. Okay. But they're not light bulbs, they're resistors. So what actually might happen is you might like touch all of them, and resistor 2 might be the hottest because it's using the most power. Okay, so let's just go through another example. So let's say this time I'm given the value of all 3 of the resistors and a current from an ammeter reading. Okay, so I don't know the voltage of the battery. So R1 is 50 ohms, R2 is 120, and R3 is 150. So I have those 3 things filled in. Okay, and then it tells me also that the ammeter reads 1.5 amps. Now you might be thinking, Narc, what current is that reading? Well, it doesn't really matter because it's a series circuit. So the current is the same everywhere. So I can fill in 1.5 amps for all of my currents. Okay, all of them. The ammeter placement in a series circuit doesn't really matter. When we get to parallel circuits, we'll talk about ammeter placement and what current it's actually measuring. But here, since the current is the same everywhere, the ammeter placement doesn't matter. It's reading the current of everything in the circuit. Okay. So since I knew all of the resistances, I said, all right, find equivalent resistance first, since I know all of that. So I add up all those resistances and get a total resistance of 320 ohms. Very big resistance. Okay. Now, that's a very big resistance with a pretty big current, right? My current in the last circuit was only 0.5 amp. So that must mean that I have a pretty big battery powering this circuit in order to push out all that current, even with this high resistance. So then, since we know the currents everywhere, and we know the resistances everywhere, I can find V battery, V1, V2, V3 using Ohm's law. And then I'm going to verify it with V battery is V1 plus V2 plus V3. So I multiplied 320 times 1.5 amps and got 480 volts, right? Because V is IR, and did the same thing going down the list. Okay. Now, 480 represents my V battery. So if I add up 225, 180, and 75, they should add up to 480. And lucky for me, they did. That's kind of what's nice about this VERT table is you have a built-in check, essentially. Okay. Then, last but not least, we can calculate the power. Now, the power equation that I've been referencing throughout this video is P equals IV, but there's also 2 other power equations. There's P equals I squared R and P equals V squared over R. Because you know, excuse me, I'm sorry for yawning. Because you know the current, resistance, and voltage for the battery, resistor 1, resistor 2, and resistor 3, it actually doesn't matter what equation you use because you know all of the parts of the equation. Usually P equals IV is the easiest because there's no squareds or anything like that. So you would just multiply this voltage times the current to get the power. Okay. So again, we see that the object with the most power, resistor 3, okay, would use energy at a larger rate. So that might be the hotter object, or if it's a light bulb, it would be the brighter light bulb. Okay. Now, this overall power is much, much larger than the total power we had in this first example. So since this power is much, 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 much larger, it's going to use energy much, much faster. So this circuit will stop working more or faster than the other circuit. Okay. And that is pretty much it for series circuit. So we've gone through and we have talked about how to solve series circuits, and we've talked about the different concepts involved in series circuits. And this should probably get you through anything you need to know with regards to series circuits. So if you have any further questions, please just let me know. I'm here to help, and I will see you guys soon. My one attendee has left, so I am talking to myself. That's always fun. All right, I'll see you guys soon. Bye.